तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the first lecture of the Module 9 on special topics. In this lecture, we shall study about composite section. This is the first special topic that we are covering in this program. First, we shall introduce the composite section, and then we shall know about the analysis of composite sections. We shall move on to the design of composite sections, and finally we shall see the analysis for horizontal shear transfer. The composite section refers to a section with a precast member and cast in place concrete. The cast in place will be denoted as CIP. There can be several types of innovative composite sections. A few types are sketched. In the leftmost figure, we have a precast web with the bottom flange. Once it has been gained the strength, it has been taken to the site, and then the top flange has been cast inside. Similarly, for the figure in the middle, the eye girder is a precast girder which has been cast in the yard, and then the top slab has been cast in the site. In the figure on the right side, the precast part is a small part which acts like a formwork, and the cast in place part is quite substantial, and here we can see that the precast member can act as a formwork for pouring the concrete for the top part. There can be different types of composite sections, and it depends on the innovation, the type of application, and the construction equipments and personnel available for producing the section. In this photograph, we can see that a precast bridge girder has been placed in the site. The reinforcement has been fabricated, the ducts for post tensioning has been placed, and you can observe that the transverse reinforcements have been projected upwards, which will act as the shear transfer reinforcement for the composite section. Once the concrete is cast and hardened, this precast girder will be transported to the site. It will be placed on the piers, and then the deck will be cast. Thus, in bridges, the composite section is extensively used, which helps us both in the construction as well as in the functioning of the member. The advantages of composite construction are as follows. First, it can lead to savings in formwork. As I had said before, sometimes the precast member itself acts as a part of the formwork, and hence the formwork can be saved. Second, it is a first track construction. If the same section had to be cast in sight, then the quality control and the time of construction would not have been satisfactory. Now, the composite construction helps us to expedite the construction, where the precast part is constructed in a controlled environment without creating any disturbance at the site, and once the precast member has been gained the strength, then it will be taken to the site for the casting of the top flange. The third advantage is it is easy to connect the members and achieve continuity. In my lecture on continuous beams, we had discussed that introducing continuity is a difficult post-tensioning operation. It can lead to substantial friction losses, but if precast members are used, then partial continuity can be introduced by connecting the post-tension cables or providing some non-prestressed reinforcement in the support region. Now, this construction is easier than trying to introduce complete continuity among the members. The prestressing of composite sections can be done in stages. The precast member can be first pre-tensioned or post-tensioned at the casting site. After the cast-in-place concrete achieves strength, the section is further post-tensioned. That means, first the precast member is prestressed in the casting yard itself, then it is transported to the site, and after the cast-in-place concrete has been placed and after that concrete has hardened, it can further be prestressed, and hence the prestressing operation is done in stages, which is based on the analysis of the different sections at the different times, and this also leads to a more efficient section. The grades of concrete for the precast member and the cast-in plate portion may be different. In such a case, a transformed section is used to analyze the composite section. If we are having two different grades of concrete, say M20 for the precast member and say M25 for the cast-in-place member, then there will be some discontinuity in the stress between the precast part and the cast-in-place part, but we can assume that the full section is of the lower grade concrete and simplify our calculations. Next, we are moving on to the analysis of composite sections. The analysis of a composite section depends upon the type of composite section, the stages of prestressing, the type of construction, and the loads. The type of construction refers to whether the precast member is propped or unpropped during the casting of the cast-in-place portion. Thus, the analysis is very much dependent on the type of composite section. Are we having a web as precast and as a flange as the cast-in-place, or is it something else? It depends on that. Next is the type of construction. That means when the concrete in the cast-in-place flange is poured, is the web being supported by some props? If it is supported, then the stress block will be something. If it is not supported or unpropped, then the stress block will be something else. Thus, we have to know what is the type of construction is being used for making the composite section, and the analysis will depend on that. The third important thing is the stage of prestressing. Are we applying the prestress at one go, or are we applying the prestress at stages? That will also lead to a difference in the analysis. The following diagrams are for a composite section with precast web and cast-in-place flange. The web is prestressed before the flange is cast. This is a common type of composite section where the web is precast and the flange is cast in place. the web is pre-stressed before the cast-in-place flange is poured. The width of the flange is calculated based on the concept of effective flange width as per clause 23.1.2 IS 456-2000. That means IS 456-2000 gives us, like, if we have a flange which is quite wide, we should take only a part of the flange in which the stress can be assumed to be uniform, and that part of the flange is called the effective width of the section. And based on that clause, we determine what is the width of the flange in our analysis. At transfer and after casting of the flange, during which the section behaves like a composite section, the following are the stress profiles for the precast web. That means, first of all, when we are transferring the prestress, the section is just the web. There is no flange at the time, and the stress block is somewhat like this. It is compressive at the bottom. There can be some tensile stress at the top, and at transfer, the loads to be considered are the prestress at transfer, which is P0, and the self-weight of the member, which is MSW. When the flange is cast, at the time the section resisting the gravity load is only the web. The flange has not gained the strength yet, and hence the moment created due to the weight of the cast-in-place concrete is carried only by the web and not by the composite section, and the effective prestress and the moment due to the self-weight is also carried only by the web portion. In this previous figure, P0 is the prestress at transfer after short-term losses, PE is the effective prestress after long-term losses, MSW is the moment due to self-weight to the precast web, MCIP is the moment due to weight of the cast-in-place flange. At service, after the section behaves like a composite section, the following are the stress profiles for the full depth of the composite section. Now we are moving on to the service load stage. By the time the flange has hardened, and the full section can now act as a composite section. Hence, the additional load that comes during the service period, that is shared by both the web and the flange, because the full section is acting like a composite section. Thus, the stress block is that due to the live load, the moment is carried along the full depth of the section, whereas the prestress and the self-weight of the full composite section is carried by the web itself, because this has stayed from the stage during the casting of the flange. That means that this stress, the stress due to the prestressing and the stress due to the self-weight of the section, has been locked in the web portion, whereas additional load that comes during the service life, that is resisted by the full composite section. There can be a variation that if the web is propped during construction, then after the flange hardens, and if the props are removed after that, then the self-weight of the member will be carried by the full section, and this is shown as the figure on the right, that if the web is propped, then the weight, self-weight is carried by the full composite section. Thus, whether the construction is propped or unpropped, this is necessary to analyze the composite section after the flange has hardened. If the precast web is propped during casting and hardening of the flange, the section behaves like a composite section to carry the self-weight after the props are removed. If the precast web is unpropped during casting of the flange, the section does not behave like a composite section to carry the self-weight. Thus, it is essential to know whether the section is propped or unpropped during the casting of the flange. From the analysis under service loads, the stresses at the extreme fibers of the section for the various stages of loading are evaluated. These stresses are compared with the allowable stresses under service conditions. That means, once we find out the stresses at the extreme edges in the concrete, then we compare them with the allowable stresses given in the code and make sure that these stresses are within the allowable values. The stress in precast web at transfer is given by the expression that we learned during the analysis based on the stress concept. The stress first consists of an uniform component which is due to the pre-stressing P0, and this is compressive. The second component is due to the eccentricity of the pre-stressing. The eccentricity is E. The moment due to the pre-stressing force is P0 times E. C is the distance of the extreme edge from the CGC of the precast web. I is the moment of inertia of the precast web, and then the third term is the term due to the self-weight of the section, where MSW is the moment due to self-weight, and the other terms have been explained just before. The stress in precast web after casting of flange has certain differences. First, P0 has dropped to PE due to the long-term losses, because usually there is a time difference between the pre-stress transfer and the cast-in-place flange construction. If the time difference is more than a month, then we can assume that the pre-stress will have substantial loss and it will drop down to the effective pre-stress. The other difference is that the moment term now includes not only the self-weight of the web, but it also includes the weight of the cast-in-place flange. Thus, the stress is given as minus PE by A, which is the uniform part, then plus minus PE times E times C divided by I, which is the part due to the eccentricity of the pre-stressing force, and the third term is plus minus MSW plus MCIP times C divided by I. This third term is due to the self-weight of the section. In these expressions, A is the area of the precast web, C is the distance of edge, whether it is the top or the bottom, from CGC of precast web, E is the eccentricity of CGS with respect to the CGC of the precast web, moment of inertia of the precast web is denoted as I. Next, we do also the analysis at ultimate. From the analysis at ultimate, the ultimate moment capacity is calculated. This is compared with the demand under factored loads. Thus, the procedure is similar to the conventional sections that we had studied earlier, that the analysis is for two stages, first at transfer and at service, which are based on elastic analysis, and then we do another analysis for the ultimate state, which is based on the nonlinear behavior of both concrete and the pre-stressing steel. The analysis at ultimate is simplified by the following assumptions. The small strain discontinuity at the interface of the precast and cast-in-place portions is ignored. As I said that when the flange is cast, there is some stress which is interlocked in the web, and due to that there is some strain in the top flange, in the top portion of the web. That means there is a strain discontinuity at the interface of the precast portion and the cast-in-place portion, but usually that is ignored in the analysis for convenience. The second assumption is that the stress discontinuity at the interface is also ignored, because the web has a stress before the casting of the flange. There will be a stress discontinuity at the interface of the web and the flange, but that can be also ignored at the ultimate stage, because the material is going into its nonlinear plastic behavior, and hence the discontinuity can be ignored at the ultimate state. The third is, if the CIP portion is of low grade concrete, the weaker CIP concrete is used for calculating the stress block. That means, if the grades of the web and the flange, they are different, then the lower grade is selected for the analysis. The strain and stress diagrams and the force couples at ultimate are shown below. That for this composite section, BF is the width of the flange, DF is the depth of the flange is cast in place, BW is the width of the web, D is the effective depth of the prestressing steel. The strain diagram at ultimate is considered to be linear based on Bernoulli's hypothesis, and the ultimate strain at the top fiber is considered to be 0.0035. XU is the depth of the neutral axis. Epsilon DEC is the strain in the prestressing steel at the decompression of concrete, and epsilon PU is the strain in the prestressing steel at ultimate. The evaluation of epsilon DEC has been covered in the analysis of members, and hence we are not repeating that calculation in this module. Now, from the strain diagram, we move on to the stress diagram. In the stress diagram, as I said, that there is a discontinuity of the stress in the concrete, but we are neglecting that. We are considering a one stress block with a value of 0.447 FCK at the topmost fiber, and FCK is the characteristic strength of the lower grade of concrete. FPU is the stress in the prestressing steel at ultimate, and again the code gives us some recommendations to find out XU and FPU, which were discussed under the analysis of flange sections. Now, once we know the stress diagram, we move on to the force diagram. We split the tension into two components. One part balances the compression in the web, and the other part balances the compression in the outstanding flanges. Now, these forces are given as follows. CUW is 0.36 FCK times XU times BW. This is available from the stress block that we have assumed for throughout the depth of the web. CUF is 0.447 FCK times BF minus BW times DF, which is the compression in the outstanding flanges. TUW is equal to APW times FPU, which is the part of the tension which is balancing the compression in the web, and TUF is APF times FPU, which is balancing the compression in the outstanding flanges. The equilibrium equations are given below. The ultimate moment capacity MUR is calculated from the second equation. The first equation is used to calculate XU accurately if you are using the strain compatibility method, and the first equilibrium is the equilibrium of the axial forces, and this equation is APW plus APF times FPU, which is the total tension, is equal to the two compressions, which is 0.36 FCK times XU times BW plus 0.447 FCK times BF minus BW times DF. This is the first equilibrium equation of the axial forces. The second equilibrium equation is regarding the moment. MUR is equal to the moment due to the first couple, which is APW times FPU times d minus 0.42 xu plus the moment due to the second couple, which is APF times FPU times d minus 0.5 df, and these equations we had used in the analysis of flange sections, and we are not going into the details of these equations in this module. Next, we are moving on to the design of composite sections. The design is based on satisfying the allowable stresses under service loads and at transfer. The section is then analyzed for ultimate loads to satisfy the limit state of collapse. The member is also checked to satisfy the criteria of limit states of serviceability, such as deflection and crack width for type 3 members only. Thus, the analysis procedure is similar to that what we have seen for conventional sections. That first, the design is based on satisfying the allowable stresses at transfer and at service. Next, we check the moment capacity and make sure that the capacity is greater than the demand under factored loads. We also do the checks for serviceability, the deflection check if the span to the depth ratio is large, and we may also check the crack width if the member is a type 3 member, and if cracking and the crack width is a concern, then we do the calculations of crack width also. Before the calculation of the initial pre-stressing force, which is P0, and the eccentricity of the CGS E at the critical section, the type of composite section and the stages of pre-stressing need to be decided. Subsequently, a trial and error procedure is adopted for the design. That means, before we can evaluate the value of the pre-stressing force at transfer and the eccentricity, we need to first be clear that what type of composite section we are using and what will be the method of construction. Once we have decided upon this, then the pre-stressing force and the eccentricity, they are determined based on a trial and error procedure. The following steps explain the design of a composite section with precast web and cast in place flange. The precast web is pre-stressed before the casting of the flange. The member is considered to be type 1 member. Thus, here we are seeing the design steps for the simple case and the more conventional case, that the web is precast, the flange is cast in place, the web has been pre-stressed before the casting of the flange, and the member is designed as a type 1 member where we do not want any tensile stress at transfer or at service. The step 1 is that after we have decided upon the type of composite section, we are computing the eccentricity E. With the trial section of the web, the CGS can be located at the maximum eccentricity E max. The maximum eccentricity is calculated based on 0 stress at the top of the precast web. This gives an economical solution. That means, we are pushing down the CGS as low as possible, satisfying the stress condition of 0 stress at top during transfer. This gives us an economical solution, and based on this triangular stress block, we can calculate the maximum eccentricity, which is E max is equal to KB, which is the depth of the bottom current point, plus MSW divided by P0, where MSW is the moment due to self-weight and P0 is the pre-stress at transfer. To remember that the CGC is the centroid of the precast web, KB is the distance of the bottom current of the precast web from CGC, MSW is the moment due to self-weight of the precast web, and P0 is a trial pre-stressing force at transfer. Step 2 is compute equivalent moment for the precast web. Let us now discuss about the equivalent moment. A moment acting on the composite section is transformed to an equivalent moment for the precast web. This is done to compute the stresses in the precast web in terms of the properties of the precast web itself and not of the composite section. Thus, the definition of the equivalent moment is for convenience, that whatever moment is acting on the composite section, we are finding out an equivalent moment such that we can find out the stresses in the precast web by the properties of the precast web itself and not by the properties of the composite section. For a moment MC, which acts after the section behaves like a composite section, the stresses in the extreme fibers of the precast web are as follows. That means, for this section which is now behaving like a composite section, let the moment acting be MC, where C stands for the composite section. Now, for a composite section, the centroid is different from the centroid of the original precast section. We are referring to the new location of the centroid as CGC prime. The distance of the top fiber of the composite section is denoted as CT double prime. The distance of the junction of the precast web and the cast in place flange is denoted as CT prime, and the distance of the bottom fiber of the web from the CGC prime is denoted as CB prime. Note that all these distances are being measured from the new centroid of the composite section. The stress block is now more difficult, and we have to understand this stress block properly, that for the composite section we have a stress at the top of the web which is higher than the neighboring fiber in the flange, and hence there is a discontinuity in the stress block which we need to consider in the analysis at service loads, and Ft is the stress in the precast web at the top and Fb is the stress in the precast web at the bottom. Now, for the moment MC, Ft is given as MC times the distance Ct prime divided by I prime, where I prime is the moment of inertia of the composite section, which is different from the I of the precast web alone, and Fb is given as MC times Cp prime divided by I prime. Again, here CGC prime is the centroid of the composite section, Ct prime is the distance of the top of the precast web from the CGC prime, C2 double prime is the distance of the top of the composite section from the CGC prime, Cb prime is the distance of the bottom of the precast web or composite section from the CGC prime, and I prime is the moment of inertia for the composite section. The following quantities are defined as the ratios of the properties of the precast web and the composite sections. So, we have two sets of geometric variables, one for the precast web and the other for the composite section. For convenience of calculation, we are taking ratios of these quantities. The first quantity MT is the ratio of I divided by Ct for the precast web divided by I prime divided by Ct prime. The prime numbers are for the composite section. Thus, it is the ratio of the moment of inertia divided by the distance of the top flange for the precast web and the composite section. MB similarly is defined as I divided by Cb divided by I prime divided by Cb prime. That means, it is the ratio of the moment of inertia divided by the distance of the bottom fiber of the web. The numerator are the values for the precast section, and in the denominator the values are for the composite section. Then the stresses in the extreme fibers of the precast web under the moment MC can be expressed in terms of MT and MB as follows. Ft is equal to mt times mc times ct divided by I is equal to mt times mc divided by A times kb. These stresses can be derived once we substitute the definitions of small mt and small mb. Similarly, Fb is given as mb times mc times cb divided by I, which is equal to mb times mc divided by A times kt. Note that the stress in the precast web Ft and Fb has been defined in terms of the properties of the precast web only, which is the A, kb and kt, provided we know the values of mt and mb. Thus, the purpose of defining small mt and small mb is to express the stress in the precast web in terms of the section properties of the web itself. Here, A is the area of the precast web, kb is the distance of the bottom kern of the precast web from CGC, kt is the distance of the top kern of the precast web from CGC. Remember that we are defining this quantity from the CGC of the precast web itself. The quantities mt, mc and mb, mc are the equivalent moments. Thus, the stresses in the precast web due to mc are expressed in terms of the properties of the precast web itself. The whole purpose of defining the equivalent moment is to have an expression of the stresses in the precast web which involves the properties of the precast web only. The properties of the composite sections have already gone into the definitions of the ratios mt and mb. Step 3 is to compute the effective prestress Pe. Let MP be the moment acting on the precast web prior to the section behaving like the composite section. The total moment for the precast web is MP plus MB times MC. If we know the moment that was acting on the precast web before the section started acting like a composite section, let that moment be denoted as MP. Next, we are having a moment MC which acts on the composite section, and in order to find out the stresses in the precast concrete, we are defining an equivalent moment which is called MB times MC, and that is added to MP to calculate the stresses in the precast web. The stress at the bottom for type 1 members due to service loads is 0. This is the definition of type 1 member, that we can have 0 stress at the bottom under service loads, and therefore we are substituting the expressions in the stress and we are substituting 0 on the right hand side. That means the resultant stress due to the effective prestress force, the eccentricity of the prestressing force, the total moment acting in the web, the final stress resultant at service for a type 1 member is equal to 0. And from this we are calculating the prestress that is required under service loads. PE is equal to MP plus MB times MC divided by E plus KT. This is the expression that is used to calculate the effective prestress once we know the eccentricity. Note that the prestressing force is acting only on the precast web, and hence E is the eccentricity of the CGS from the CGC of the precast web. As I said before, that if the precast web is prestressed before the top concrete has hardened, then the prestress is carried by the web only, and hence when we are calculating the stresses due to the prestress, we are still using only the properties of the web part, and the eccentricity is measured from the CGC of the web. The fourth step is to estimate P0 from PE. This is done as follows, that it is 90% of the initial applied prestress, which is Pi for a pre-tension member, 90% because we are considering the elastic shortening for a post-tension member, since the elastic shortening occurs during the application of the pre-stressing force, and if the tendons are stretched simultaneously, in that case we can consider that P0 is equal to Pi, which we are measuring by the jacks for post-tension members. Now Pi can be AP times the 80% of the characteristic strength FPK, and AP is calculated from the effective pre-stress, that PE divided by about 70% of the characteristic strength will give us the value of effective pre-stress. Thus, once we know the effective pre-stress from the previous expression, we can calculate the amount of steel that is required by estimating an effective pre-stress of 70% of the characteristic strength. From the amount of pre-stressing steel, we are calculating that what is the maximum possible pre-stressing force at transfer based on the maximum pre-stress during transfer, which is 80% of the characteristic strength. Like this, we can estimate P0 from PE that we have calculated in the previous step. Step 4 then continues as revise E, the location of CGS, as given in step 1 based on the new value of P0. We had seen the expression of E in step 1, and we can revise the calculation of E based on the new value of P0. Step 5, check for the allowable compressive stresses in the precast web. At transfer, the stress at the bottom is given as follows. Again, this is the expression that we had seen earlier during the analysis. The stress FB should be limited to FC allowable, where FC allowable is the allowable compressive stress in concrete at transfer, and which is available from figure 8 of IS 1343. At service, the stress is given as Ft equal to minus Pe by A minus Pe times E divided by A kb plus the total moment Mt plus the equivalent moment of Mc divided by A kb. The stress Ft should be limited to Fc allowable, where Fc allowable is the allowable compressive stress in concrete under service loads, and this is available from figure 7 of IS 1343. If the stress conditions are not satisfied, then we have to increase the area of the precast web, that is A. Step 6 is to check for the allowable compressive stress in the CIP flange. That means, till now we have checked the stresses in the web, but now we are checking the stresses for the flange. Ft prime, which is the maximum compressive stress in the flange, it is given as Mc, which is the moment acting in the composite section, times C2 prime divided by I prime. The stress Ft prime should be limited to Fc allowable, where Fc allowable is the allowable compressive stress in concrete under service loads for the cast in place flange. Another important consideration for a composite section is the analysis for horizontal shear transfer. With increase in the load, the bottom face of the cast in place portion tends to slip horizontally and move upwards with respect to the top face of the precast portion. To prevent this and to develop the composite action, shear connectors in the form of shear friction reinforcement is provided. That means, since the precast web and the cast in place flange are trying to deform together, there is a tendency of slip at the interface, and the web may deform more than the flange, and there is a chance of a vertical separation at the interface. Now, in order to check the horizontal slip and the vertical separation, we provide interface reinforcement, which is called shear friction reinforcement. The required shear friction reinforcement per meter is calculated as follows. ASV is equal to 1000 times BV times tau h divided by 0.87 Fy times mu. the minimum requirements of shear friction reinforcement and spacing are similar to that for the shear reinforcement in the web. Thus, this expression gives us the amount of shear friction reinforcement that is required, but the minimum values and the maximum spacing, they are governed by the web reinforcement. In this expression, ASV is the area of shear friction reinforcement in millimeter square per meter, BV is the width of the interface of precast and CIP portions, tau H is the horizontal shear transfer at the interface in Newton per millimeter square, Fy is the yield stress of shear friction reinforcement in Newton per millimeter square, mu is the coefficient of friction at the interface and equal to 1 for intentionally roughened interface with normal wet concrete. Thus, before laying the cast in place flange, the interface is intentionally roughened so that there is a good friction between the flange and the web. The shear friction reinforcement in the web can be extended and anchored in the cast in place portion to act as shear friction reinforcement as below. That means we do not need additional shear friction reinforcement. The shear reinforcement that is used in the web is extended beyond the web so that when the concrete in the flange is cast, that shear reinforcement acts as the shear friction reinforcement. Thus, in this sketch, BV is the width of the interface, and you observe that the shear reinforcement has been extended above the web and it is within the flange, and the interface has been intentionally roughened to have a friction between the cast in place concrete with the precast concrete. Let us now understand the analysis of a composite section by the help of an example. The mid-span section of a composite beam is shown in the figure, which is to follow in the next slide. The precast web 300 millimeter times 920 millimeter in depth is post-tensioned with an initial force P0 of 2450 kilonewtons. The effective prestress PE is estimated as 2150 kilonewtons. Moment due to the self-weight of the precast web MSW is 270 kilonewton at midspan. After the web is erected in place, the top slab of 150 millimeters times 920 millimeter in width is casted unpropped, producing a moment MCIP of 135 kilonewton meter. After the slab concrete has hardened, the composite section is to carry a maximum live load moment MLL of 720 kilonewton meter. Compute stresses in the section at various stages. Thus, for this particular section, the web is precast, the width is 300, the depth is 920, the CGS is located 200 millimeters from the bottom of the web, and then after the post-tensioning operation has been done, the concrete in the flange has been placed, during which the web was unpropped, and the width of the flange is 920 millimeters and the depth is 150 millimeters. The initial prestress, the final prestress, those values are given, and we have been asked to find out the stress conditions at the different load stages. First, we are calculating the geometric properties. For the precast web, the area is given as 2.76 times 10 to the power 5 millimeter square. I is equal to 1.95 times 10 to the power 10 millimeter square. Distance of CGC from bottom is half of 920, which is 460 millimeters. For the composite section, we have another set of properties where A prime is equal to 4.14 times 10 to the power 5 millimeter square, I prime is equal to 4.62 times 10 to the power 10 millimeter square. Distance of CGC prime from bottom is 638 millimeters. Note that the area of the composite section is larger, the moment of inertia is larger, and the CGC prime has moved upwards due to the placement of the flange. Thus, the calculated values make sense with our intuition that after the section behaves like a composite section, the moment of inertia will be large, the centroid will also shift up. Second is calculation of stresses in web at transfer. From that conventional formula, we are placing the values of P0, area of the precast web, I of the precast web, C is 460 for the top and bottom fiber of the precast web, and the self weight of the precast web is also given. Once we substitute these values, we get the stress of minus 0.22 Newton per millimeter square at top fiber and minus 17.54 Newton per millimeter square at bottom fiber of the web at transfer. That means we have now calculated the stress condition of the web when the prestress is transferred to the section. The second step, the next step is the calculation of the stresses in the web after long term losses. That means before the cast in place concrete has been poured, we are recomputing the stresses in the web considering the drop in the prestress, and with the effective prestress equal to 2150 times 10 to the power 3 newtons, we are having a stress of minus 0.97 Newton per millimeter square at the top and minus 14.61 Newton per millimeter square at the bottom. This is the stress condition in the web just before the casting of the flange. The fourth step is the calculation of stresses in web after casting of the flange. Now, once the flange has been cast, we have to add the moment due to the weight of the cast in place flange. That means the first two terms remain same as the previous load stage. It is in the third term where we are making a change. We are bringing in MCIP, which is the moment due to the weight of the cast in place flange. And once we substitute the value of MCIP, we get the stress of minus 4.16 Newton per millimeter square and minus 11.42 Newton per millimeter square at the top and bottom respectively of the precast web. Next, we are calculating the stresses in the composite section at service loads. Now, the flange has hardened, the live load is acting, and we are finding out the stresses under the service loads. First, we are calculating the stresses due to the moment due to the live load. At the top fiber of the flange, Ft prime is given as MLL times C2 double prime divided by I prime. Once we substitute the value of MLL, C2 prime we can calculate from the location of CGC prime, and I prime is the property of the composite section. We find Ft prime is equal to minus 7.01 Newton per millimeter square. This is the stress at the top of the flange. At the bottom fiber, the value is Fb is equal to MLL times Cb prime divided by I prime. Note that we are using the properties of the composite section for the live load moment. And once we substitute these values, we find out Fb is equal to 10.36 Newton per millimeter square. Calculation of stresses in the composite section at service loads will now include the calculation at the top fiber of the precast web also. This is calculated from the proportionality of the triangles. We know the stress at the top of the flange, we know the location of the CGC prime. From this, we can calculate the stress in the web at the top fiber of the web, and that is given as Ft is equal to the stress at the top of the flange, which is 7.01, divided by the depth of CGC prime, which is 432, times the distance of the top of the web from CGC prime, which is 282. This gives us a stress at the top fiber of the web as minus 4.57 Newton per millimeter square. Once we have calculated the stresses due to the live load, we are now adding them with the stresses that has been locked into the web to get the total stresses under service loads. For the precast web at top fiber, the total stress is given as minus 4.16, which was there during the casting of the flange, minus 4.57, which has come from the live load moment, the total stress is minus 8.73 Newton per millimeter square. At bottom fiber, it is minus 11.42, which was there during the casting of the flange, plus 10.36, which is the tensile stress due to the live load, which gives a resultant compressive stress of minus 1.06 Newton per millimeter square. For the total stress in CIP slab, the total stress is due to MLL only. Note that the CIP slab does not take any stress from the prestressing force or the self weight because it was an unpropped construction. The only stress that comes in the CIP slab is due to the live load only, when the whole section is behaving like a composite section, and hence the calculations remain same as that for the live load, that Ft prime at the top is minus 7.01 Newton per millimeter square, and the bottom stress is the same that we calculated for the top fiber, the precast web, which is minus 4.57 Newton per millimeter square. Once we plot the stress profiles, we understand the effect of the composite section. At transfer, we had a stress profile like this. There was substantial compression at the bottom, very little compression at the top, almost negligible. Then, after losses, the stresses have dropped, the compressive stress at the bottom has reduced, as well as the stress at the top has slightly increased because of the drop in the prestressing force. Now we are casting the concrete, and after the casting of concrete, again we find that the precast web is carrying the weight of the flange and the stresses have increased. Due to the live load, we have a full composite section resisting, and we are able to find out the stress in the top of the flange, at the interface, as well as at the bottom of the composite section. And finally, we get the resultant stress block, where we are adding up the stress that has been locked in the web, plus due to the live load, we get a stress in the web, and the stress in the flange is same as that due to the live load. Thus, the final resultant stress block is minus 7.01 in the flange, minus 4.57 in the flange at the interface, then minus 8.73 at the web near the interface, and minus 1.06 at the bottom of the web. Thus, in today's lecture, we covered the composite sections, and we first saw that there can be different types of composite sections based on construction, based on the stages of prestressing, based on the materials used, and the analysis is based on all these factors. We had also studied the principles of analysis of composite sections. We need to calculate two sets of properties, one for the precast section and one for the composite section. Then we also understood the principles of design, where each steps are similar to that of a conventional section, but we have to be aware of the different properties. And finally, we also learned about the analysis of horizontal shear transfer, which is taken care by the shear friction reinforcement. And we understood these principles by using an example. With this, we are ending the module on composite sections. Thank you.